Hello everybody, my name is Daniel Megastab, and this presentation is for Physics 2211, Lab 2 on projectile motion. The goal of this lab was to compare experimental motion with computational predictions. First, I recorded the projectile's motion using the stationary camera. Next, I analyzed the video using Tracker to obtain the ball's position as a function of time. Using those measurements, I created a computational model based on Newton's second law. I first assumed gravity was the only force acting on the ball, then created a second model that included air resistance. Finally, I compared both simulations to the experimental data to determine which model best represented the actual motion. This slide shows the experimental setup used to collect the data. The projectile was an earth ball with a mass of approximately 0.050 kilograms. The ball was thrown horizontally across the camera's field of view while the camera remained stationary throughout the experiment. A MacBook with a known length of 0.313 meters was used as a calibration object so Tracker could convert distances in pixels into meters. After calibration, Tracker was used to mark the position of the ball frame by frame and generate position versus time data that would later be used in the computational model. Tracker data analysis. This slide shows the results obtained from Tracker. The horizontal position versus time graph is approximately linear and is described by the equation x equals 2.73t plus 0.08. This indicates that the horizontal velocity remained nearly constant during the motion. The vertical position versus time graph follows a quadratic equation y equals negative 5t squared plus 1.51t plus 0.488. This parabolic relationship is expected because gravity produces a constant downward acceleration. These equations allowed me to determine the initial position and velocity that were used as the starting conditions in the GlowScript computational model. Gravity-based computational model. Using the Tracker data, I created a computational model in GlowScript. The model uses Newton's second law, where the net force acting on the ball is equal to the gravitational force, which is mass times gravitational acceleration. The initial position and initial velocity were taken directly from the Tracker measurements, and gravity was the only force included in this first simulation. Air resistance was fully ignored. The resulting trajectory produced the familiar parabolic path expected for projectile motion under constant gravitational acceleration. Drag-based computational model. For the second model, I added air resistance, also known as drag. Drag acts opposite to the direction of motion and reduces the object's speed during flight. Rather than calculating the drag coefficient directly, I adjusted the value until the simulated trajectory most closely matched the trajectory measured in Tracker. The value that produced the closest agreement was approximately b equals 0.002. Because the ball traveled for only half a second and had a relatively low speed, adding drag produced only a very small change in the trajectory. Comparison of experimental and computational results. This slide compares the experimental trajectory with both computational models. All three trajectories follow nearly identical parabolic paths. The gravity-only model already agreed very well with the experimental data, and adding drag produced only a slight improvement. This indicates that air resistance had a very little effect on the motion of this projectile over the short flight time. The total flight time was approximately half a second, the maximum height was about 0.6 meters, and the horizontal distance traveled was about 1.4 meters. Any remaining differences between the models and the experimental data are likely due to the sources of experimental uncertainty. These include manually selecting the ball's position in Tracker, slight calibration errors, uncertainty in the estimated drag coefficient, and small variations during the throw. In conclusion, this lab demonstrated that projectile motion can be accurately modeled using Newton's second law. The Tracker analysis provided experimental position and velocity data that were then used to build computational models in GlowScript. The gravity-based model closely matched the experimental results, while the drag model produced only a slight improvement since air resistance had very little effect on the short duration of the projectile's flight. Overall, the computational model successfully represented the experimental motion, showing that Newton's second law provides an accurate description of projectile motion under these conditions. Thank you for watching.